Thanks. I'll begin. Heavenly Father, we thank you for this day. Again, Lord, I thank you for the students. I just pray you'd just bless this class today. Help us to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. All right, so let's see here. Recap. Well, let's say it this way. Solutions of d, did I do plus or minus lambda last time? Minus, okay. So d minus lambda to the power, say, n. So if I let this operator act on y equal to 0, the solutions are y1 equals e to the lambda x, y2 equals to x e to the lambda x, dot, 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 yn equals x to the n minus 1, e to the lambda x. These were solutions to that differential equation, right? We figured that out. And then the thing I started talking about at the end of class was solutions of d minus alpha, quantity squared, plus beta squared, acting on y. Let's suppose that's to the power n again, equals to 0, are y, well, let's say z1 equals to e to the lambda x, z2, x e to the lambda x, dot, 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 zn equals x to the n minus 1, e to the lambda x, but these are complex solutions. So here we're saying lambda is alpha plus I beta, with beta not equal to 0. These are complex solutions. So, for example, the jth one of these, right, zj would be, x to, let's say, I guess it's j minus 1 for what it's worth, but x to the j minus 1, e to the lambda x, right? But we can work out what is that actually? That's x to the j minus 1 times e to the alpha plus I beta times x, right? But what's that? That's x to the j minus 1 e to the alpha x cosine beta x plus I x to the j minus 1 e to the alpha x sine beta x. This right here is the so-called real part of z to the, zj, the j solution. And without the I over here, this is the imaginary part of zj. All right? So we're not looking for complex solutions. We're trying to construct a real solution, right? So complex solutions are nice because the same mathematics, essentially, that found the real solutions finds the complex solutions. But, oh well, they're not quite what we want. So to find what we want, we use that theorem I went over last time, which says that every complex solution to a homogeneous linear real differential equation contains within it two real solutions, the real and the imaginary part. And in fact, we can prove that those are linearly independent. Not that I will in here, but you could. So long story short, we take these n complex solutions, and from these we extract 2n real solutions. What are the 2n real solutions in this case? The analog of this, so we get y1 is e to the alpha x cosine beta x, y2 e to the alpha x sine beta x, y3 e to the x e to the alpha x cosine beta x, y4 x e to the alpha x sine beta x. All right, you see where I'm going with this. And so forth and so on until finally we get to y 2n minus 1 is x to the n minus 1 e to the alpha x cosine beta x. And then finally the 2nth solution, y2n x to the n minus 1 e to the alpha x sine beta x. This is everything that can happen. It's either a repeated linear factor or it's a repeated irreducible quadratic factor, right? These are algebraically different things. And they produce quite different looking solutions, right? Exponentials versus exponentials times sines and cosines, right? And then we get multiplication by x for repeated things. Yeah. Now, so that's the general how to find solutions to this kind of thing, right? But usually we have combinations of these, right? So like, example 1. So let's try to solve d squared plus 1 squared times d minus 1 cubed. So this, what does this give me? This gives me a cosine, a sine, a x cosine, and x sine from that. Why? So this is, I'm saying lambda here is equal to 0 plus I. Right? So like d, oh, come on, this marker's worthless. D squared plus 1 is d minus 0 squared plus 1 squared. I'm about to give up on this marker here pretty soon. But then again, it's been sitting in my garage for about 3 years, so go figure. So we have this repeated irreducible quadratic, right? Yeah, I don't know about that. Is everyone on board with me why those 4 things appear as solutions corresponding to that factor? So what doesn't make sense?
I don't know. I have a hard time following.
Ah. I guess I just have to say accept this on faith for now then. It is this case. It's just that when alpha is 0, this is d squared. And beta squared, so it's d squared plus 1 can't be factored over the reals, which means I get sines and cosines from it. Because I have d squared plus 1 squared, we pick up x cosine and x sine as terms from the fact there's a square. If we're looking at a kth order operator, we should expect like k independent solutions from that operator. This is a 4th order operator, right? So that's why I got 1, 2, 3, 4 things. Now, d minus 1 cubed, on the other hand, this one, oh, come on. See, it's teasing me. Like there's some, so this is lambda equals to 1, right, which is real. I'm sorry, did I say lambda equal? Yeah. So d minus 1, right, this is d minus lambda cubed, right? So according to the general recipe, which we derived last time, we should get e to the x e to the x, and x squared e to the x as solutions for this. If I plug these functions into this operator, I get 0. I'm just repeat what you said. I'm sorry.
Because the d inside of the bracket is not square, so we look at the cube right outside.
Right. So this versus this, these are very different things, right? If we had this, well, that would be, which is something else. Details matter, yes. Okay, fine. So these are our 7 solutions that we get for the 7th order problem. And so the general solution is C1 cosine x plus C2 sine x plus C3 x cosine x plus C4 x sine x plus C5 e to the x plus C6 x e to the x plus C7 x squared e to the x. That will be the general solution to this 7th order differential equation. What if I had something like d squared plus 4d plus 3 times d squared plus 6d plus, I don't know, 11. X and y equals to 0. I want to find the general solution. What would this look like in prime notation, by the way? You get a, this is d to the 4th, right? Plus how many d cubed? 6. Looks like I got 10d cubed, right? How many d squareds do I got? 11, 21, 24. How many d's do I got? Looks like I got 18 plus 44, 54, 62. Correct me if I'm wrong. I'd appreciate it. Plus 33. You're like, you're wrong to even try this. If that's what you're thinking, get out. Sorry. No, just kidding. No. It could be worse. There's a professor at NC State who teaches calculus, and they're like, you know, the calculus 1, right? So you learn the fundamental theory of calculus in there, and he would tell the students, like, after you take my class, I come up the hallway and I ask you, what's fundamental theorem of calculus? And you don't tell me right away, like, what it is. You just don't tell me, I'll kill you. This professor is hilarious, though. He's well known. He, like, all of his, long before it was common, before the age of selfie came upon us, his you know, his photographs for the department were always with him taking, like, a, you know, he had a camera out here and like that. All of his, he was taking selfies before it was before it was in. So this monstrosity in prime notation would look like this, right? The 4th derivative plus 10 y prime 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 plus 24 y prime prime plus 62 y prime plus 33 y equals to 0. We're solving this differential equation right now. But I started us out with an easier thing because it was already the factoring is the thing that's the hard part, right? You're like, so you might give me this on a test and expect me to factor it? Not without other details, no. I mean, if I give you this and I give you a couple of hints, it becomes a reasonable problem. Let me show you what a reasonable hint would be in a second here. But so this, what? This factors, right? This does not. This, when we complete the square, we get this, right? So you can look at it like this. This is lambda equals to minus 1. This is lambda equals to minus 3. And this one right here is lambda equals to minus 3 plus or minus 2i. But I'm going to choose the plus because I can. So once I recognize that, I use the things we derived last time, and I write down the answer. And I'm wrong. So there's an error I made here. All right, you guys tell me what it was. Square root of 2 is what I was looking for. This is the square root of 2 squared, right? So I need square root 2 here. Watch out for that, right? It's beta squared that has to appear here. So I was supposed to have, square root of 2 times x, square root of 2 times x up in there. That was the error. So what hint would make this problem accessible? How could I? So suppose, let me call this thing star. So I could say this: solve star given that y equals to e to the minus 3x cosine square root of 2x is a solution. That becomes a reasonable problem. Although challenging, more challenging than example 1, of course, because it requires some thinking. So what does it mean if e to the minus 3x cosine root 2x is in the solution? This says, right, this being a solution, that says that lambda equals to minus 3 plus I root 2 is a, let's say, characteristic root of star. I just used that term for the first time in here. I will explain it further in the next few minutes of lecture, okay? But let's say that that's a characteristic root of R, which means what? That means that there is a d minus 3 squared plus 2 in L, right? So if imagine yourself in the world where we weren't given the blue equation, right? We're just given star. If I call this thing L of y, then that says that there's a d minus 3 squared plus 2 in the factoring of that, yeah.
How do you know it's squared if you're giving
And d plus 3. That wasn't your question, though.
The d plus 3 is squared if you're just giving cosine as a solution? So that's
You're asking what if it was sine?
yeah, like how do you know that it's squared? Like you would only know that it's squared if you saw that sine was also a solution.
I could have plus 17 e to the minus 3x sine root 2x. Wouldn't change a thing. The point is that when we're solving this kind of differential equation, the way that I get sines and cosines is from complex zeros in the factoring. So if I have a cosine times an exponential, I can work backwards. I can go, aha! If I have root 2 times x, that means my beta was root 2. And if I have alpha times, in this case, minus 3 times x, that means that my alpha was 3. I mean, I've lost track. Minus 3, I think, yeah. 3, I'm stupid. Anyway, this differential operator has that and also that as solutions. So if I plug in either of these functions into this, I get 0. What is it? Yep.
Now, I think what she's asking is like, is there a possible solution to only the stuff that you wrote in red? Like, yes, it also includes the sine x, but is there a solution to just the cosine? Like, how do we know there's...
Because what we worked out last time is that if we have a constant coefficient differential equation, if you have a sine solution, you also have a cosine solution. They come in pairs. They're the real and imaginary parts of the complex exponential solution. So you can't have one without the other for a constant coefficient problem. To get just a sine solution and not a cosine solution, I don't know. I'm not sure I could do that for a differential equation. I'd have to work hard at making that happen. So if this, which is what? D squared plus 6D, right? 6D, good grief, I can't. 6D plus 11. If this is a factor of L, how would you find the other factor? Long division. So you just do d to the fourth plus whatever, I mean, 10d cubed, 24d squared, 62d, 33. And I divide by the thing I know is a factor. If I haven't made an arithmetic mistake, and I'll start us out, d squared looks like I made a mistake, huh? Oh well, there's a mistake in here. Anyone know where it is?
D squared times 11 and D squared times 3.
So can you fix it for me? Which number of these? Which one of these numbers is wrong? Is my question. Which one?
24 D squared. I think that's supposed to, well, I don't know. It's like D squared times 11 and D squared times 3 would give you an extra 14.
3, 21, 21 plus 11. 32? What'd you guys get? How many d squareds? 3 plus 24 is 27, 27. Oh, 38. Yeah, I agree with you guys. That's supposed to, I missed something. I missed a term. I think I missed the, I don't know what I missed. Anyway, that's supposed to be 38. Thank you. So 38. What happened? 38 minus 11 is, what is it? 27. Oh, but I've I also can't do math. That's 4d squared, right? I think that was my larger problem, but that's 4d cubed. There were two mistakes I was making. Now they're fixed. So 4d, so I'm supposed to do what? Plus 4d, that's better, yeah? So I get 4d cubed plus 4 times 6, 24d squared plus 44d, subtract, it gives me 3d squared minus 18d plus 33. Oh, cool, plus 3. I mean, if we did this right, it ought to give us a remainder of 0. So I shouldn't say it's impossible to give you a fourth order problem without it being factored. It's just if I give you a fourth order problem, I have to give you something else that allows you to factor it, right? But this is a differential equations class, so to make it interesting, I should give it to you in a slightly circuitous fashion, like tell you that something's a solution. If I tell you something's a solution, that speaks to the existence of an operator in the factorization of the problem. Again, always using this recipe that we derived last time, which I wrote over here. Okay, let's try this again. I'm going to play this game a little bit different. Whoa. Yeah. See that? That's a marker near death. Another marker near death. Near death. Near death. Near death. Whoa. It's a good thing I brought the juice. All right, so the game I want to play with you guys is I'm going to give you a function, all right? You're going to tell me what operator picks this function up as a solution. So this is reverse. This is backwards solving. Okay, so here's the game we're playing. Given y equals to stuff, all right, find, let's say, a, which is, some polynomial in the differentiation operator, all right, and I'll stick with x for the moment, such that a of, stuff equals to 0. And we want a to be minimal. In the sense that we want to make it like the lowest order differential operator we can get away with, right? And have this work. So here, let's play this game. So here's my y, and you guys are going to tell me what to put in a over here. I'm going to start out small. E to the x, e to the minus 2x, cosine of 11x, e to the x sine x, x squared cosine x, and finally x cubed plus x e to the minus x. There we go. So what am I trying? I want what? I want this a acting on e to the x to be 0. What should I make a? D minus 1. If you didn't understand that right now, what they're doing is they're going back and they're using what we worked out last time. They're just reading basically my lemma 4 or 5 backwards, right? That's all. This one, d plus 2. Very good. This one.
D squared plus 121.
D squared plus 121. We have a winner. Yes. So this is he got that from lambda is equal to 11i, right? And 11 squared is 121. Everyone knows this.
How's it break it back down to 11 in reverse there? Where's that rule at?
We're using the, the basic case here is d minus alpha squared plus beta squared acting on y equals to 0 has, this is the case we use most often, y equals e to the alpha x cosine beta x and y2 e to the alpha x sine beta x. These are fundamental solutions to this problem.
So I got that. I was looking at the beta squared that messed me up. How you came back up to 121. I got you.
Oh.
That was my brain.
It's okay. Now, how about this one? Here we got, what's our characteristic root? 1 plus I, right? I'm just looking at this. I mean, that's alpha equals to 1, right? Alpha equals to 1, beta equals to 1. This is just pattern matching. That's all I'm doing. D minus 1. But if it's pattern matching, you don't know. It's magic, right? It's magic you need to learn, though. How can I get x squared cosine x? What's the lowest order constant coefficient differential equation which takes that as a solution? Sixth order. But your heart's in the right place. See, sixth order, because in order to get the x squared cosine x, you already had to have like x, you already have to have a cosine, a sine, an x cosine, an x sine, and then finally you get the x squared cosine, x squared sine. So it's sixth order. It's a sixth order problem. And this one, let's see here. So this is just lambda. This is coming from lambda equals to I, three-peated. Three-peated, technical term right there. So that would be d squared plus 1 quantity cubed. Again, we can't just get cosine. They come in pairs. Yeah. Yeah. This one. Now this one is requiring another idea. So if I have to kill x cubed, right? That's just lambda equals to 0 4 times, right? So like d to the fourth acting on x cubed is equal to 0. I think you could have told me that without building the larger machine that we have this week, right? I mean, you know the fourth derivative of a cubic is 0. I'm just saying, under our umbrella of thinking, I see that as the characteristic solution 0 repeated 4 times. That's where that's coming from for me. I'm always thinking about the recipe going backwards. Now, this x e to the minus x is lambda equals to 1 2 times. I'm sorry, not 1, minus 1. Repeated, right? So this piece I can kill with d plus 1 squared. That acting on x e to the minus x is 0, right? Again, going back to last class, I was like lemma 6 or something. So how do I want to have my cake and eat it too, right? So how can I make sure that this a makes both of those things go to 0 at the same time? What do I do? It's a logical and, right? Multiply. So this is just d to the fourth times d plus 1 squared. That'll be what I want for that one. You need to work problems from like section 4.1, 4.2, and 6.2, I think, until you're bored with this stuff, right? Wait a minute. I should say until Dr. Smith warns me, I shouldn't say until you're bored with it, because there exists the chance that you're bored already and you'll take this advice in the wrong way. I think Dr. Smith usually says, do the homework until it hurts and then do 2 more, something like that. But, okay. So this thing I'm showing you, what we're doing right now is we're finding the so-called annihilator. I used this a is actually the annihilator of these functions. The annihilator of e to the x is d minus 1. The annihilator of e to the minus 2x is d plus 2. The natural annihilator of cosine 11x is this. That's the annihilator of e to the x sine x. This is the annihilator of x squared cosine x. This is the annihilator of that guy. An annihilator is a differential operator which kills the function. It sends it to 0. Yes. It deals it a mortal blow. All right. Now, putting the cart before the horse a little bit, we don't actually, I mean, the theory needs to catch up, all right? I've gotten the calculations got a little bit ahead of the theory at the moment. But the reason I'm doing this is because I usually go on, I do theory for another 30 minutes, and then I eventually come back to this. By the time I come back to this, we're so far divorced from this that you guys don't know what I'm doing. So I thought, maybe, just maybe, I'll try this semester to do annihilators right after I show you the solution set in the hope that more of you get it. Now, some of you still haven't gotten it, and that's okay. You need to do homework. That's what homework is for. So that said, let us go on to the theory. You're like, what theory? Well, remember I talked about linear independence? So we need to talk about linear independence and the existence and uniqueness theorem, all these fun things. So let me get to that. If you're paying attention, you realize I've already shown you how to solve an arbitrary, homogeneous, constant coefficient differential equation, right? We have a method. We write down the operator in terms of, we write down the differential equation in terms of operators. And what do? Factor the operator if we can. If we can't factor it, then we're stuck. Fair enough. But we factor the operator. And then we write down n solutions according to the recipe. Either we have repeated real case, we have repeated irreducible quadratic case, and we can write down the solution set from those. I hope I've showed you enough examples that it starts to make sense. It won't really make sense until you work some problems for yourself. Now, there's one other thing I've neglected. The thing I've neglected is the characteristic polynomial. I should talk about that momentarily before I get back to the theory. But if we have, let's say, d to the n plus an minus 1, d to the n minus 1. I really should have written this up the other day when I had everything on the board already. D squared plus a1d plus a naught. All of this thing, right, acting on y equals to 0. AKA what? In the prime notation, this is what? yn plus an minus 1, y to the n minus 1, a2 y prime prime plus a1 y prime plus a naught y equals to, we don't even have to have 0 over here. See, this could have something else. We could have, I think I usually, you could have a g. You could have g over here like that. Right? This is the so-called inhomogeneous term. AKA forcing function. We have not talked about how to deal with that yet, right? We've only been looking at the case g equals to 0. If g equals to 0, I've described how to solve these at the moment. Okay? But given this differential equation, constant coefficient differential equation, the characteristic equation is lambda to the n plus an minus 1, lambda to the n minus 1 plus da 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 plus a2 lambda squared plus a1 lambda, a2 lambda squared rather, plus a1 lambda plus a naught equals to 0. In other words, this is the characteristic equation. So you can also look at all of our results in view of the characteristic equation, right? Because another way to say what I said today is to say you look at the characteristic equation and you calculate its roots. If you have real roots, you do exponentials times x's. If you have complex roots, you do sines and cosines, possibly times exponentials, possibly times x's, depending on the specific structure, right? So, like, for example, what example am I on? 3? Oh, okay. Kind of unexciting. Here's one. If I have y prime 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 minus 81 y equal to 0, right? I can write down the characteristic equation, which is lambda to the 4th minus 81 equal to 0. And then I can factor that. So this tells me that lambda is 3, lambda is minus 3, or lambda is equal to plus or minus 3i, right? And then we can write down the general solution, right? What is it? We have e to the 3x, e to the minus 3x, plus c3 cosine 3x, plus c4 sine 3x, right? Warning. So it is also true that we have d to the 4th minus 81, right, is equal to what? It's equal to d minus 3 times d plus 3 times d squared plus 9. That's also true. This differential operator factors in this way. Right? It's true. Well, what don't we have? We certainly cannot say d is equal to 3 minus 3 or plus or minus 3i. If you write this, it offends me. I take it personally. Like, do not write this. It hurts me when I see this written. You're telling me the differential operator is telling me that d dx is 3. No! d dx is not 3, right? Lambda can be 3 because lambda is a variable, right? d dx is a fixed operator. So when I factored this, I was using a theorem to identify the lambda from the theorem, right? This is equivalent to solving the characteristic equation, finding its zeros, and writing down the answer. Two different paths to the same set of data. Yep.
Lambda plus 3.
Oh no, have I done that? Let's see here. Yeah, it's supposed to be a plus. Sorry about that. Other questions? Yes, the rules of algebra didn't just suddenly change just for this example. No. Yeah.
Okay, so the d and the lambda, aren't, like, you can't like say they're kind of the same.
They have the same algebra. Like whatever factorization you find, I mean, the fundamental identity which links these two things is this. If I take a polynomial in the differentiation operator and I let it hit e to the lambda x, guess what happens? I get the polynomial in lambda e to the lambda x. That's the fundamental identity linking these two worlds. So if it's the case that the polynomial in D acting on a function makes it 0, and that function is exponential, then it's also going to be the case that that same polynomial in lambda must be 0. Like if this is equal to 0, right, that means that the p of lambda has to be 0. So they are similar, but not the same. All right, I think I blathered on too long about this stuff, so I'm going to have to put the theory on the board here for a bit. But well, let me just try to write more before I do that. Where am I? Oh, there it is. So definition, if we have functions f1, f2, fn, these are linearly independent. Which I will forevermore write as Li, right? Linearly independent, if and only if, well, if whenever C1F1 plus C2F2 plus plus CNFN is equal to 0, this implies that C1 is 0, C2 is equal to 0, Cn is equal to 0. In other words, functions are linearly independent. Functions are linearly independent if there's no linear dependence amongst them. There's no way to write one as a linear combination to the others. That's equivalent to what I'm writing here. Here, these C's are real numbers, okay? To be clear, here, C1, C2, we're thinking of them potentially as being real numbers. And this is an equation of functions. So this is actually a function equation. On, and oh, I'm sorry, linearly independent on U, which is some subset of the reals, okay? So that means that this has to be, I don't know, there's the only way I know to really explain this concept further. Here's a clarifying example. If I have x, and if I have absolute value of x, all right? These are linearly independent on the reals, all right? But they're not linearly independent on, say, 1 to 2. So why is that? So if you, so from 1 to 2, we have x is positive, right? So that means that absolute value of x is equal to x, right? So I can take c1x plus c2 absolute value of x equals to 0. And if I just let c1 be c1 equals to 1, and if I let c2 equals to minus 1, you know, I've got 1 times x plus minus 1 times x is equal to 0. But of course, 1 and minus 1 are not 0. Consequently, x and absolute value of x are linearly dependent on the interval 1 to 2, right? But over here, if I have that c1x plus c2 absolute value of x are equal to 0 for all x in the reals, that's a different thing. See? Because then I can take x equals to 1, and that gives me that c1 plus c2 equals to 0, and I can take x equal to minus 1, and that gives me that c1 minus c2 is equal to 0. Two equations, two unknowns, different slopes. So these you can solve, and the solution is c1 equals to c2 equals to 0. So the point here, graphically, guys, is that x looks like this, right? Absolute value of x looks like that. And so they're not the same graph, unless you just focus here or here. Like if I look at x, absolute value of x, you know, for x less than 0, for some interval with x less than 0, it's linearly dependent again because absolute value of x is equal to minus x. So the concept of linear independence depends on the domain in question, in principle. In practice, this isn't really an issue for us, so I'm sorry I just wasted 5 minutes of your time. Sorry. So let's see. You're like, this is seems very mathy, right? Mom, Jenny asked my son Daniel if he liked me helping him with math. I think Daniel told Jenny that I was too mathematical. Such withering criticism. But we would like to find a more calculational way to understand linear independence, right? So here's how to do it. So suppose y1, y2, yn are linearly independent, right? That means that on some subset of the reals, okay? That means that we've got c1y1 plus c2y2 plus plus cnyn equals to 0. But this is a function equation, right? So what can I do to a function since calculus 1? Differentiate, right? So if I differentiate this equation, I get c1y1 prime plus c2y2 prime plus cnyn prime equal to 0, right? If you can differentiate once, you can differentiate twice. Just keep differentiating, right? Keep differentiating. Eventually, we'll get the c1, the n minus 1th derivative, like so, right? And then what I'm looking at is n equations in n unknowns, right? The unknowns are C1, C2, Cn, right? If these functions are linearly independent, that means that the only solution is what? I mean, these are simultaneous equations, but we already know what the only solution which is allowed by linear independence is what? The zero solution, right? By definition, we have to have C1 through Cn are all 0. So my question is, what does that require of the functions, right? We're looking for a necessary requirement for these functions if they are going to be linearly independent, right? So I can rewrite this as y1, y2, yn, y1 prime, y2 prime, yn prime, y1 to the n minus 1, y2 to the n minus 1th derivative, yn to the n minus 1th derivative. This matrix, n by n matrix of functions, times the constant vector c1, c2, cn, this is equal to 0. Now, some of you have had linear algebra, some of you have had 221, some of you have not. But one of the things you'll learn in there is if you have a matrix times a vector equals to 0, and only 0 is the solution to this equation, right? That means that the coefficient matrix must be invertible. More pragmatically, that means that the determinant of that coefficient matrix has to be 0. So this matrix here, the determinant of this is called the Wronskian of y1, y2, yn. So to check linear independence of a set of functions, what we can do is take them, put them in a matrix, take the derivative, second derivative, how many derivatives we need, make a matrix, take the determinant of that matrix. If that determinant is non-zero, all right, at even one point, then on the interval where that point is contained, they have to be linearly independent. Let me illustrate. Yeah. So suppose we want to prove like cosine and sine are linearly independent. So the Wronskian, let me call this y1. Let me call this y2 so I don't have to keep writing that. The Wronskian of y1, y2, and we usually use like a semicolon x for the argument. That's going to be the determinant of y1, y2, y1 prime, y2 prime. If you don't know what a determinant is, that is unfortunate, but I have formulas for 2 by 2, 3 by 3, and even 4 by 4 determinants in the notes. I encourage you to look at those. I'm not going to write them on the board because it would be a waste of your time and mine. But this will be, let me be more explicit here. What's y1? Cosine x. What's y2? Sine x. What's y1? Oh, minus sine x, right? Cosine x, derivative of sine, right? Check it out. Cosine squared x plus sine squared x is the determinant there, which is 1, right? So therefore, cosine x and sine x are linearly independent on the reals. There was no condition on x at all, right? Does that make sense? Hey, here's one that's kind of might be bothering you. How about, what if we look at like x times an exponential? Let's do that one too while we're at it. Let's do a 3 by 3 there because you guys need to see a 3 by 3 determinant. So rather than writing out the formula for an arbitrary one, let me just do an example with a 3 by 3 determinant so you see that. I think that's more useful for you guys. Again, if you've never seen determinants and like to have me tell you more about them, happy to tell you about in office hours or whatever. But otherwise, you should take linear algebra. You'll learn more there. There are lots of things known. But let's calculate the Wronskian of, let's say, we'll keep it easy, e to the x e to the x, x squared e to the x. All right? At x. So this would be the determinant. So we put in the top row, we put the function. In the next row, we put the what? Derivative of the function. So that's going to be e to the x. I'm going to keep the e to the x factored out, but this is 1 plus x, yeah? And this one over here is e to the x times 2x plus x squared. Then we take another derivative. Two plus x, I think. You guys correct me if I'm wrong. Did I get that right? The 3 component here is x squared plus 4x plus 2 times e to the x. I just like to verify that before I go on. Do you guys agree? Okay. Fun fact, the determinant, we can factor out the e to the x. We have e to the x cubed. Determinant of 1x x squared, 1 plus x, x times x plus 2, 1 x plus 2. Is that factor? I don't know. I don't really care. X squared, I probably should care, but I don't care. X squared plus 4x plus 2, like that. So you can take this determinant. E to the x cubed is e to the 3x. This determinant, it's 1 times x plus 1 times x squared plus 4x plus 2 minus x times x squared plus 4x plus 2 minus x times x plus 2 plus x squared times 1 times x plus 2 minus x plus 1. I'm expanding across the top row using Laplace's expansion by minors. For example, this x, since it's in the middle, gives me the minus, right? And the things that are not there are this and that, which gives me 1 times x squared plus 4x plus 2 minus 1 times x plus 2, right? I think I'm missing a big old parenthesis like that. If I know what's good for me, I'll just leave it there and say that's not 0. So, yeah. I mean, we should actually simplify that, right? To complete the thought. So I'll multiply it out because I don't know any better. Is there anything common here, actually? Is there, oh, look at this. There's some cancellations that go on here, aren't there? Like, for example, I've got, see this? I've got x times x squared plus 4x plus 2, right? Minus x times, so these two terms be canceling. So I've got e to the 3x, x squared plus 4x plus 2 minus x squared times x plus 2 plus x squared. Let's see, this is what?